why should limnologists care about salinity? Well, virtually all lakes have some amount of salt in them, even the freshest lakes. And while most of the world's lakes are freshwater, some of the largest and most charismatic lakes on Earth are saline. So I'm standing here on Lake Fryxell in Antarctica, and it has fresh water in the Epilymnion, but brackish water in the bottom. And the dry valleys of Antarctica are actually known for saline lakes. Just up valley is Lake Bonney, and to the north of me is Lake Vanda, which is meromictic, and the hypersaline bottom water is over 20 degrees Celsius. And next to Lake Vanda is Don Juan Pond, the second saltiest body of water on Earth.
All major ions are essential to sustaining life in inland waters, and salinity is of major importance in the osmotic regulation of metabolism and in the distribution of biota. The salinity of lakes and rivers is predicted to increase in the future due to climate change, human activities, and heightened demands for freshwater resources. The term salinity refers to the mass of dissolved inorganic solids found in water. It is therefore important in limnology for its influence on water density and stratification, as well as for its chemical and biological effects. Salinity comprises numerous ions and molecules, but for most limnological purposes it is considered the mass fraction, milligrams per kilogram, or mass concentration, milligrams per liter, of the major cations, sodium, magnesium, calcium, potassium, anions, chloride, sulfate, and carbonate species, bicarbonate, carbonate, that are dissolved in the water. Because salinity is dominated by charged ions, it can be approximated by electrical conductivity. This is a measure of a solution's ability to conduct electron flow and is expressed in microsiemens per centimeter. Conductivity is highly temperature dependent and is therefore usually corrected to a set temperature and reported as specific conductance. Lakes range in salinity from almost pure water in glacially fed lakes to a record-setting pond in Ethiopia that is 12 times the concentration of seawater. Given this large range of salinities in inland waters, it is useful to differentiate freshwater from saline water, although there is no ecological basis for such an exact threshold. Nevertheless, for practical purposes, the boundary between fresh and saline water has generally been accepted as in the range of 1 to 3 grams per liter. Lakes with salinities greater than 3 grams of salt per liter are referred to as saline lakes, and those of non-marine origin are termed athalasic. A classification system for athalasic saline waters was produced by Hammer, 1986, and ranges from freshwater, less than 0.5 grams per liter, to hypersaline, greater than 50 grams per liter. Hypersaline waters are found on every continent on Earth. Well-known examples include the Great Salt Lake, the Dead Sea, and Don Juan Pond. This large variation in ionic composition has led limnologists to try to find commonality amongst the diversity of systems. One approach, the Gibbs model, delineates the roles of rock weathering, atmospheric precipitation, and the evaporation-precipitation process. Over large regions of the temperate zone, the ionic composition of lakes tends to mirror that of rivers, with dominance by calcium and bicarbonate ions. But in lakes more so than rivers, salinity is influenced by evaporation, biotic and abiotic losses from the water column, and by equilibrium and exchange with the sediments. In addition, there are many coastal lakes where ionic composition has evolved from trapped seawater. Weathering of soil and rock is the dominant source of ions for many inland waters. Chemical weathering reactions include the alteration of minerals, as in this example 1, and also includes the complete dissolution of minerals, as in example 2. Both of these reaction pathways lead to the formation of ions, which are leached and transported to aquatic environments. Atmospheric deposition can also be an important source of salinity. This delivery of ions is largely through wet deposition by rain or snow or fog. But in arid regions, dry deposition of salts, that is direct fallout in the absence of precipitation, can exceed wet deposition. Back to Dr. Hilary Dugan, who, in addition to her studies on Antarctic saline lakes, has a broad interest in the causes and effects of salinity change in inland waters. Dr. Dugan is an associate professor at the Center for Limnology at the University of Wisconsin-Madison, and here describes some of the human impacts on salinity in lake and river ecosystems.
Human activities have wide-ranging effects on ion contributions and the salinity of inland waters. Human-derived ion inputs come from the exploitation of geological resources, agricultural intensification, industrialization, and urbanization. Point source pollutants include industrial outflows, wastewater effluent, and mining waste. A notable point source pollutant that quickly became globally pervasive was the industrial emission of sulfur and nitrogen compounds, namely from the burning of fossil fuels by power plants. And while we've gone a long way to reduce point source atmospheric emissions, there are still areas of the globe where atmospheric deposition of ions is a large contributor to the ion balance in freshwater bodies. Non-point source pollutants of major ions are equally prevalent. Agricultural fertilizers and livestock manure applied to cultivated lands leach ions to surface waters. In many urban cold regions, road de-icing salt, typically in the form of sodium chloride, as applied to impervious surfaces, has resulted in the salinization of many lakes and rivers. For instance, Lake Mendota in Madison, Wisconsin, has seen chloride concentrations increase from 2 to 3 milligrams per liter in 1940 to upwards of 50 to 60 milligrams per liter today. A similar analysis of Lake Constance, a large 254-meter deep European lake, revealed a threefold increase in chloride concentrations. About half of this ion input was from road salts, 23% was from wastewater, 11% was from farming, 9% was from soil weathering, and precipitation and solid waste incineration took care of the remaining 3%. Climate affects the balance between precipitation and evaporation, and therefore the salinity of surface waters. In closed drainage basins, the salinity of lake water is governed not only by the inputs of dissolved ions from runoff, but by the fate of these materials upon evaporation. As water evaporates from a lake basin, ions become concentrated and the salinity increases. Closed basin lakes, termed endoreic lakes, that are exposed to periods of severe aridity may evaporate completely or sufficiently to expose large expanses of sediment. Diversion of water inputs by human activities, as in the tragedy of the Aral Sea, can also lead to the exposure of large areas of sediment. It's expected that increasing evaporation and a decrease of precipitation driven by climate change pose a salinization risk for many water bodies, and this is especially true for closed basin lakes. Many of the world's great closed basin lakes are also saline lakes, like the Great Salt Lake in Utah. If these lakes dry, they can pose a human health risk from blowing dust that may contain dangerous toxins, such as arsenic.
Saline lakes host important biodiversity, and they are often key habitats for migratory waterbirds. In addition to this biological richness, saline lakes may also have remarkable geological and geochemical features. A striking example is here at Mono Lake, California, where limestone towers that formed underwater in the past had been exposed by falling lake levels. Mono Lake has also proven to be an excellent place for collaborations in limnological research, as described here by Drs. John Melack and Bob Jellison at the Sierra Nevada Aquatic Research Laboratory at the University of California, Santa Barbara.
Another hallmark of our work here has been a lot of collaborations with people from all over the country. For example, there was a microbial observatory here run through the University of Georgia, which studied the very complicated dynamics of the bacteria which are living under high hydrogen sulfide conditions, high ammonium conditions. There's also work by USGS where they looked at the metabolism of arsenite with another redox reaction for bacteria. You've also collaborated with who else, Rob?
Well, avian researchers, JPL, most researchers that came here, we'd hook up with at some point to provide them some baseline data or to help them with their sampling and things like that.
In all lakes, monitoring salinity and the concentration of individual ions is important for understanding lake physics, chemistry, and biology. Ion concentrations in a lake will vary both temporally and spatially. In this example, temporal changes in specific conductance are a result of winter road salt inputs and ion rejection from a growing ice cover, and summertime precipitation of calcium carbonate. Here in Lake Kinneret during summer, there is depletion of calcium and bicarbonate ions in the epilimnion due to precipitation of calcium carbonate, CaCO3, and buildup of these ions in the hypolimnion caused by partial resolubilization of this precipitating carbonate. When the lake mixes in winter, the water column is reset and becomes isohaline. The ability of freshwater biota to tolerate variations in salinity varies greatly among and within species. Few freshwater species are truly euryhaline, that is, able to tolerate a wide range of salinities. In ecosystems threatened by freshwater salinization, the impact of increasing ion concentrations on the biota is complex and depends on many environmental and evolutionary factors. Much of the beauty of inland waters lies in their diversity, and this includes their enormously diverse range of salinities. From the dilute lakes of the Canadian Shield to the salty Caspian Sea, the salinity of inland waters is scientifically complex and globally important. As lakes and rivers worldwide are confronted with climate change and other human pressures, there is risk of losing inland water systems that are critical to biodiversity and to human well-being.